our next speaker. I'm not sure you've seen him today. No, his name is Kyle Davis. He's a head of developer advocacy or something like that at our organization. And what he's going to show us today is yet another module that we've been developing. Perhaps you've heard of it. It's called RediSearch. So please, Kyle.
Hey, everybody. I wanted to say a couple of different things. I'll be introducing a couple of controversies throughout this this session. And one of this is on this slide here. One, I failed to put up the actual conference slide, so you don't see RedisDay London. I apologize deeply for that. I realized that while I was sitting in that chair right over there. The other thing is not RediSearch. It posed a lot of problems when we put this thing together. There was two S's, and they kind of pushed them together. So if you see that and somebody says, "Oh, I use RediSearch," it's RedisSearch. It's been my personal thing to talk about constantly whenever I say that. So you're not wrong. It could read as RediSearch. And Redis Labs, in our previous logo, it's changed a little bit. It was all one font, and people would sometimes say, "Do you work for Redis Labs?" And no, we don't work for Redis. So anyway, I want to talk a little bit about this. I'm not the creator of RediSearch. I'm not the father of RediSearch. Sometimes you hear that. Roy would be considered maybe the father of Redis Graph. Salvatore would be the father of Redis. I didn't write RediSearch. I was with RediSearch, and I watched it grow up. So I like to say I'm the uncle of RediSearch. I know a lot about it. I've been there from its infancy, but at the same time, I can't claim creation of it. So this is going to be a very familiar slide, too. It's slide recycling. I think good engineers are intrinsically lazy, and so I'm intrinsically lazy, so I recycled this. But it does. I want to reiterate this. So first we had Redis, and Redis could do some great things. It was lean and mean and all that sort of thing, and people had their itch that they wanted to scratch. Salvatore came out with the modules ecosystem where you can plug directly into Redis and create your own functionality of whatever you wanted to do. And one of the first ones that happened was RediSearch. Now, this is the logo for RediSearch. And like I said, I'm kind of the uncle of RediSearch, and I've been around it for a long time. But this logo, I looked at it, and when I first saw it, I said, OK, that's fine. It's the logo. It looks good. It's very similar to Redis. You got the red stacks here and everything. I had no idea why there was a stack of frying pans. Evidently, just I think a couple weeks ago, Itamar was like, "I designed that. How dare you say anything about it?" That is my fault. That's magnifying glasses, guys. I was completely wrong about it. So yeah, the stack of magnifying glasses. So RediSearch is a full-text search engine, and secondary indexing is what it can do as well. And full-text search engines are something people get confused. Is it a web crawler? No. You provide it data, and then you can take that data, and that data can be kind of structured, semi-structured, that sort of thing, or just text. I mean, it can find things in it. So let's see how this looks. Take a look at it. Full-text search, and then secondary indexing. Full-text search. When we talk about this might be, you have articles in a newspaper, and you want to find any time that they said Redis, right? And it would look through all the full-text search and find that. So secondary indexing, when we talk about this, we're talking a little bit more about, let's say that you have a slow database that you can retrieve things from, but it's not indexed in a way that you want to find things. And that can be very painful or slow, and you don't want to implement another thing. You can use RediSearch to kind of augment that other data store and find information in, because it can be very flexible. So example, you might want to find users with a specific shoe size that live near Bozeman, Montana in the US. Well, that would be a great thing to do if you just had something that was storing, let's say, just JSON files or something like that. So you can do both things here. So how do we do that? What's the kind of components of it? This is kind of what RediSearch is. It does a couple different things. Well, three things, but a couple things are related. Search and aggregations, and they share the same query engine, right? So that means that when you're doing search and query, if you want to find things in it, Query is going to be the same between those. And they're joined here because they use the same storage engine internally. But it can do a third thing, which is the autocomplete engine or suggestion engine. Now, I put it outside the Venn diagram here because it actually uses an entirely different storage system. And we'll get to why that's really cool and why that's a really good choice. Autocomplete is that, as you type, you hit a key, and then it brings you back the results as you type. It has to be very quick and can retrieve things very simply. Let's take a look at the data lifecycle. And when I say RediSearch here, this is primarily the search and aggregations, right? So the first thing you're going to do is you're going to create a schema. Now, that's weird in Redis, right? Like, you generally don't create schemas. Redis graph is the maybe exception here. We have 4 types. We have text, which would be full text. It's a variable length, anything that you want that would be in a human language. Numeric, which is a number of undefined size. That's important too. We optimize for whatever the maximum size is inside of it. A tag field. This is one of the more complicated things to describe. It's a very simple concept, but I think people get caught up in it. Tag fields in RediSearch are effectively like a collection of flags or data flags. So the example that I tend to use is, let's say you are looking at all the foods in a store, right? All the foods in the grocery store. You would then tag it if one is, let's say, kosher, one is vegan, one is pescatarian, so on and so forth. You could have multiple of those things be true, right? And that'd be a great use case for something like tag. And then it has geospatial capabilities, so you can plot things on our globe that we have here. And it doesn't, if anybody here is a flat earther, it doesn't work for you. The mathematics here are for a globe. So the other thing you have to do is you add documents. After you create schema, you can add documents in real time. And that means that when you add documents, there is no practical delay between the document being added and it being available in query. So you can add things directly. So what that means is you can just say, hey, RediSearch, here's a document. And we have the command ft_add, just like set or whatever in regular Redis. You can also have a hash that you already have in Redis and say, I want to just add it from the hash. And then finally, the thing that you can do, and this comes into play when we're talking about a lot of times in the secondary index use case, you can index only. And that's really interesting. With index only, what you can do is you can actually take the document, and you don't have to store the document. We only index it. So it can save you some space there. If you don't need to retrieve it, you'll be retrieving it from some other system. And then after you've added documents, you can then search and aggregate on top of it. Now, you can add documents at any point after you've created schema, and you can search at any point after you created schema, but if you're going to search and do aggregations, you kind of have to have documents first. And you can delete documents as needed, and that can happen at any time as well, and it's always up to date. So there's no delaying in the indexing. And finally, you can drop the whole index if you want to at the end, and then you can't add documents after that. That would be kind of weird. So let's talk about how it looks in search and query. Now, because it is a full-text search engine, it operates very differently than Redis. It has its own query language. Let's take a look at it. I'm going to show you a few attributes of that. So when we were looking at this, what were the goals? The first thing we wanted to do is intentionally not be SQL, right? No, that's not what we want to do. That tends to get people itchy, and they decide to do weird things with it and write page-long queries and that sort of thing. That's not what it is, because it's a search engine. It's a different use case. We wanted it to be familiar enough for people to not have to spend hours and hours and hours learning it. But we needed to be exposable to end users in some pretty simple way. That's SQL. You have to prevent against injection attacks and that sort of thing. So it needs to be something that an end user could actually look at and kind of discern what's going on. So without having administrative commands or anything buried into it. So pretty simple. That's how we wanted it to look as well. And the cool thing about search engines, and this is the thing, when you're searching something, let's say you're going to your favorite e-commerce store and you're typing something in, you don't know what the underlying database looks like. So one of the markers of a search engine is that you have no knowledge of what's going on underneath it, right? So we also wanted to be powerful enough that even though it's simple and you need no knowledge, you can also find things very precisely. And yeah, let's look at an example of this. This is a valid query in RediSearch, just right there. What this will find is documents that have both forward and truck in any text field, okay? But we can make it a little more complicated. Let's take a look at that. Here's kind of the things we support. Your logical operations, Exact phrase matching, which would be here, your in quotes type of thing that you're probably familiar with. Geospatial, obviously we have to be able to specify lots of different things here. Tags, prefix, number ranges, and optional terms, optional terms allow you to move things up in the results, not necessarily dictate what's returned. So let's take a look at this, and I'll walk you through a fairly complicated one. It's a little bit US, North American centric. First, we're going to find Chev, which will find Chevy or Chevrolet with the asterisk. That's a prefix search. We have an or here, which is represented by a pipe. Ford, we've put it in brackets to indicate that's kind of in a sub part of it. We don't want to find anything that is Explorer, so we have to find a Chevrolet, a Chevy, or a Ford. It's not an Explorer. Optionally, we want it to be a truck. So if it's truck, it will go up in the result count rather than be at the bottom. We want between year 2001 and 2011, so that's a numeric range. The location is 7440 within 100 kilometers, so 100 kilometers from New York City. And we support all the miles and inches and that sort of thing. And the condition, this is a tag, so condition equals good or very good. So that's a valid but fairly complex query. Let's take a look at how other things that we can put into the full text search. We implement stop words. Stop words are words that are so frequent in the document they have no indexing value. So a fox in the woods, we would just really index fox in woods internally. Then we have stemming. So we're finding effectively the root of a particular term. Query going, it would find going, go, and gone because we're looking for anything that matches it. And if you look at this, it's not necessarily, there's linguistic rules that go with this, so we can have different languages that also match it. Slop. Slop is an interesting one. What slop does is has intervening terms. So if you query glass pitcher and you indicate a slop of 2, we're going to look at things that have intervening terms. Glass and then gallon beer pitcher, there's 2 terms between it, it will still find it. And then content, the context here. Okay, so let's say we're looking in Shakespeare, right? If you type in to be or not to be, do you want to return the entire play? Probably not. So what you can do is you can do highlighting, which will basically say, okay, I'm going to add a specific HTML tag or whatever you want to the thing that's found. So you can see I've specified that. That's the highlighting bit. And then summarization, so it's going to find things surrounding that term as well. So you don't have to return the entire, 200-page play or whatever it is. Some other ones we have. Synonyms. You can specify synonyms. So if you search for Bob, you will also find Robert. You specify that yourself. You build that yourself. Spell checks. So did you mean? And if you type FXO, it will find an 11-gene distance of 1 here. So it will do the auto correction there if you want it to. And then phonetic search. It uses the double metaphone algorithm to find John Smith would match J-O-N-S-Y-M, S-M-Y-T-H. If I could know my letters, that would be good. So you have all these different features here that you can see that we're kind of being a little smart with the documents. Scoring. This is a little bit confusing, and I'm going to gloss over it a little bit. But you have a few different things. You have a field weight, so some fields are more important than others. And then you have a document score, and that's a reference of the quality of the document. And we have scoring functions that allow you to develop that score. So you take the score, and then you do something with it. We have a few different ones. TF, IDF is what we use. Term frequency, inverse document frequency. It's very well known. It's pretty great, actually. But we have other options. Doc norm, normalization of the doc score, if I can recall correctly. BM25, Dismax. Solar is another full-text search engine that uses Dismax. You could just go by the raw doc score, or you can use Hamming distance with the binary payloads. There's a way to put a binary payload in, but it's way beyond the scope of this talk. So if you're doing independent sorting, you can say sort by a specific field. Then you don't. Then it's completely trumping any of this stuff. So lots of different ways to look at that. So let's take a look at aggregations quickly. The aggregation engine is relatively new. We've had it for probably 3 or 4 months now. Aggregations, basically you process and transform results from a search, and it uses the same query language. So you put your query in, and you change the command. We're altering some stuff in the syntax for the next version, the next major version, but that's to be determined, so that some things may change here. You can group, sort, and apply transformations and it's a pipeline of composable actions. So example here, we have apply a couple different times. So you can build these kind of complex grouping and reductions, and then they can go in any of these orders, so you can put together pretty complex things. All right. So we have a number of reducers. Do want to point out my favorite, count distinct-ish. We use a probabilistic structure to find, if you're wanting to trade speed for exactness, we have count distinct, which will be the exact amount, and to count distinct-ish. It's my favorite. But you have the normal players, average, standard deviation, that sort of thing. And then we can manipulate strings in various different ways. For example, substrings, these are expressions that we have here. We can do complicated formulas with arithmetic. We can even work with timestamps and be able to convert them using kind of the standard percent sign syntax that you see. And I think this ends from like Perl, if I recall correctly, where it kind of all got started. But it's pretty well known, these different identifiers inside that will extract different parts of a date from a Unix timestamp. So let's take a look at how FT aggregate works. So this is going to be an example of both a query and a search, right? So first up, FT aggregate. Our index here is called shipments. That's where all the documents have all been indexed under shipments. First thing we're going to look at is box area, and that's our field. And this is a numeric field, and we're saying between 300 and positive infinity. If you're familiar, that might look pretty similar to how the sorted set syntax works in Redis. You're right, it's pretty similar. So that's our query. The first line's our query part of it. If we were to change this to FT search, then it would have the exact same results. It would just return all the documents that contain a box area between 300 and everything above that. So we're going to apply this expression here. So we're going to take the timestamp, shipment timestamp, which is a field in our document. We're going to divide it by 1,000 because it's a millisecond precision timestamp, and we want to get a second precision one. And then we'll get the year out of it. And then we're going to create a field called shipment year. Pretty simple. Then we're going to group by. RediSearch uses this kind of similar pattern in all of its commands. You'll see group by one shipment year. So what it's saying here, the one indicates that you only have one variadic argument after that. So group by one shipment year, and then we're going to reduce the count. The count has no arguments, that's why it says 0 as shipment count. So that would be able to start taking the number of the counting by the year and reduce them and saying how many are per year. So how many came in 2011, 12, 13, 14, so on and so forth. Then we're going to sort by that. So that's a pretty standard sort by. We're going to sort by shipment count, which was produced in the previous part of this composable action. And we're going to do it in descending. That probably looks pretty familiar. And then we're going to limit it to 0, 3. So we're going to get the first few results. And then we're going to apply a text transformation here. So we're going to format. We got this again. So it says percent sign, excuse me, I'm getting thousands of shipments, right, in this. So we're going to say, OK, percent 1,000 plus shipments. So that's a string. So here's where we're actually making the calculation. We're going to floor this, mathematically floor it, so we're not going to get anything. We're going to take a look at the floating point and go down. The shipment count divided by 1,000 and as shipment count. So this would output actually a readable 3-line result out of it that would say, these are the shipments, how many thousand shipments we had per year. So in essence, that's the whole aggregation engine. I want to take a few minutes to talk about autocomplete. We're a little bit crunched on time, but autocomplete's really cool in RediSearch. The thing about autocomplete is it works differently than most autocomplete engines do. Some people have this idea with autocomplete that you just add the data and then you autocomplete off the data that you had, your entire data set. Well, that's not great. Then you do a prefix search on that. Now, if you start thinking about the complexity there, that's really heavy and maybe not something you want to do because it's everything in your data. So maybe there's a better way. The thing about this is the frequency of words in all your documents may not actually be very good as a search query. When you're looking at something, a user types something into a box, and they actually want to get a search query completion there if you really start thinking about it from an aspect of a full-text search engine. And the frequency doesn't indicate quality either. So is there a better way? Can we actually use what the users have instead of this expensive and slow method? So the other thing is that I won't get into it a whole lot, but you can provide extra context. So if you're used to Google and you're auto-completing, it will put, for example, stuff that you've previously searched in the autocomplete before something brand new. So that's context, and you wouldn't have that if you're just using this kind of out-of-the-box thing. So RediSearch uses a radix tray. It stores a collection of suggestions at a single key, and each suggestion has a score, kind of like the document. And finally, when a user, basically I say you can use anything with a search box and when users interact with a result. So simple API, it's got 4 commands: ft-such-get, ft-such-add, ft-such-del, and ft-such-lin. So get, add, delete, and get the length. 4 commands, pretty easy. So how do you use this is the interesting part. So you have a search box that you have on your application, and you would do ft-such-get, and then you put the user's input into that, so what they're typing their search in, okay? Then what you would do, you have the results. Instead of going directly to the results, like when a user clicks or interacts in some way, then you would go in and actually put that through a RediSearch forwarder, a forwarder that goes through RediSearch. So when you define a search hit or miss, is that somebody clicking or buying, however it might be, you use ft-such-add. So in this way, you're taking that user input and then you're incrementing it by 1. So that means that the user's input is actually directing itself. So that's all I got today, guys. Sorry I had to rush through the last bit of it. RediSearch is really great. You should check it out. RediSearch.io is a place to look for more. Thanks, everybody. It still works.